All right, well,
Oh, yes,
hello everybody. My name is Mike Yaley. I'm the director at the Lair, the Bear.
There's Alex.
And I just want to start by saying thank you. We have 150 people who signed up to participate today. We're really excited about our virtual guest speaker program, and tonight is our first one. And just a couple of housekeeping items. We will be muting everyone. So please, if you happen to unmute yourself, don't be offended if we mute you back. We will be recording this video, and I believe you acknowledged that in the sign-up sheet. So if you don't want to be on the recording, please just turn your video off. And then questions. Alex will go through his presentation, and then we will have questions. So please put your questions in the chat. We're going to transfer those to a spreadsheet that I will have access to after the presentation, and then I will go through the questions and hopefully get through as many of them as we can in a reasonable amount of time. And so with that, I'd like to introduce our speaker. Alex Filippenko joined the UC Berkeley faculty in 1986, one of the world's most highly cited astronomers and an elected member of the National Academy of Sciences. He's co-authored nearly 1,000 papers, has been given numerous prizes for his research. A winner of the top teaching awards at Berkeley and selected by students a record 9 times as the best professor on campus. He was named the 2006 Carnegie Case National Professor of the Year among doctoral institutions. He's produced 5 astronomy video courses with the teaching company, co-authored an award-winning textbook, and appears in over 120 TV documentaries, including more than 50 episodes of the Universe series on H2. In 2004, he received the Carl Sagan Prize for Science Popularization. An avid tennis player, hiker, snorkeler, scuba diver, whitewater rafter, and skier. He enjoys world travel and is addicted to experiencing total solar eclipses, and so far has 17 under his belt. Please welcome
about that. I clicked on the wrong button. Can you hear me? Yeah.
Yes.
I clicked on the wrong button and stopped the recording somehow. So I didn't mean to do that. Anyway, let me get to my own screen here. For some reason, Mike, your screen is gigantic. Oh, there we go. All right. Well, that works, I think. Good. Is everyone still okay? Everyone can hear me? Yeah. Okay, good, good. All right. We had some technical difficulties there. Well, welcome everyone. And I'm sorry that we're not going to be at the Lair this summer, but you can see my background, right? Can everyone see my background there? That's from last year's show. So and I see I can't spell here. It should say Astro Department, UC Berkeley. Oops. I was missing the Lair so much that I couldn't even figure out how to spell. So anyway, it's really fun to be able to at least give some talks despite the fact that we can't be there this summer. And normally I would start with this, Go Bears slide and then tell you about, if it's a Sunday night, I would tell you about the star party that's coming up on Monday. Well, you know what? This time there's not going to be a star party after Disco Bingo, so boo-hoo. However, there will be Disco Bingo, as you saw in the email message that the Cal Alumni Association sent out. So I'm looking forward to participating virtually. And then next year, or whenever we can get together again, we'll try a star party and, looking at the moon and looking at Jupiter, which is a giant planet, Saturn with the beautiful rings, Alberio, a binary star, the Cal star because of the blue and gold colors, a cluster of stars. These are some of the favorite objects we look at when we have star parties up there. Another cluster of stars. A dying star, this one called M57, the Ring Nebula. There's the dying star in the middle there. Anyway, a galaxy, the Whirlpool Galaxy, that's always a favorite. So we'll take a look next year whenever we can go up there in person again. So anyway, that's the way it goes. I hope everyone's safe and feeling okay. Those of us who haven't gotten a haircut in 4 months, they're looking kind of shaggy like I am now, but I've decided to maybe just let it grow until basically things open up fairly safely. We'll see how that goes. I might not do that. But I hope everyone's safe and that your friends and families are safe as well. Stay well, and it's a small price to pay, you know. Okay, well, I'd like to tell you this evening about the University of California's Lick Observatory. It's really a wonderful facility that does all kinds of research and public education and technology development and the training of students. It's just 14 miles as the crow flies east of San Jose. And it was built at a time when there wasn't much of anything in the great San Francisco Bay Area. Now, of course, there are big cities and lots of lights. And so we have to appropriately tune our research to not be affected very much by the city lights. And I'll have more to say about that later. But there it is. You can see it. And some people have driven up there or taken your bikes up or whatever.
Hey, Alex, you need to share your screen. It's not shared with the group right now.
Oh, how come you didn't tell me earlier?
I didn't want to butt in. I didn't
No,
know
but
if
I
you
was
were ready.
showing. Oh, well, then I have to show all my things again. Bummer. Okay, just a second. Well, then in that case, you know what I'm going to do? I'm going to fix the typo. Next time I do something stupid, let me know, okay? So where do I go to share my screen? I mean, this is a very visual talk, so if I don't share my screen.
Usually at the bottom, there's a button you push that says share screen.
All right, let me go to Zoom. I have to probably go to Zoom. I have to probably bring up zoom.us. Yeah, Mike, listen, I'm not easily offended. Tell me when I'm doing something stupid, okay?
I wasn't sure if you were sharing it yet. My apologies.
No, I was sharing it. I even said I had a misspelling. I had Astro was, so what, under preferences maybe?
Just at the bottom of your screen, your Zoom, it should say share screen or share content. Just whatever you clicked before we got on with the group.
Okay. Share screen.
There you go.
Am I shared now?
No, not yet.
This is really bizarre.
I promise we had this worked out before everybody got on.
Yeah, we had it before everyone was on. Shoot. Well, this is really strange because I typed in share screen. Let me go advanced. Right, I'll tell you what. If I exit and then enter again, we'll have it. Want me to do that?
If you think that'll solve the
Yeah,
problem,
because
that'd
this
be
has
great.
happened. This happened once before, and the only way I could get it to work was to exit and then enter again. That's what I'll do.
Okay.
All right, I'll leave the meeting and then I'll enter it again. So you guys got to let me in. Okay. So now, how do I exit?
We'll let you in, we promise.
How do I exit this meeting? Sorry about this, folks. This is the first time
Click
we're
on
doing
it, and
this.
then should be a leave
click
icon
leave.
in the top right.
Or lower left, or lower right.
Well, again, I'm not seeing anything having to do with Zoom. That's my problem, is that, oh, here we go. Oh, there's share screen. Is that working? Watch this. Ha-ha.
There you go, you got it, you got it.
Hey, look at that. Okay, well, listen, let me just, no, I didn't want to do presenter view. I wanted to do just regular view and show. Come on, just play from current slide. There we go. Can everyone see that now?
Nailed it. Good job. You're good to go.
Yay. Okay, so now I will start, and I'll say, I'm sorry we're not all there, but go Bears. No star party after disco bingo. We like to look at the moon and Jupiter and Saturn and the Cal star and a cluster of stars and another cluster of stars and a dying star. Can you all see me? I see Mike doing something weird there. Yeah. And a galaxy. Okay, great. Back to my talk. You know, we'll still have enough time for Q&A despite the late start here, folks. Sorry about that. Okay, so University of California's Lick Observatory, 14 miles east of San Jose. In 1888, when the first big telescopes were completed, it was the world's first modern mountaintop observatory. And you could say that it was really the birth of big science in the US, certainly west of the Mississippi, okay? And it was made possible by one James Lick, about whom a lot of interesting things could be said. Let me just shorten that and tell you that he arrived in San Francisco, Yerba Buena at the time, in early 1848, coincidentally, just 3 weeks before the discovery of gold at Sutter's Mill. Now, James Lick couldn't have timed it any better than that, okay? Well, like many others, he decided to try his hand searching for gold. But after just a few days of that, he decided that he didn't like to literally get his hands dirty. He was a wealthy man because of his previous ventures, and he enjoyed a much more relaxed and refined life. So he decided to figuratively deal with the land, that is, with real estate. And what he did was he purchased much of the land in the San Francisco Bay Area from people who were willing to sell it at a very low price to go off to seek their fortune. And then when people started coming back from the Sierras and also from the East Coast to California during the gold rush a year later, he was very happy to sell them back the land at a gigantic profit. So San Francisco went from a little shanty town, I'm not sure where I had of a missing photo, but it was just a little shanty town. No, there it is, yeah, in 1848, to a booming metropolis of about 30,000 just 3 years later. And that land had been sold to the people by James Lick. So he became a very, very wealthy man, okay? A lot more than just the money I show here. And he had no natural heirs. He had one bastard son with whom he didn't get along. He thought he was a lazy good-for-nothing. So near the end of his life, he was wondering what to do with his wealth. And he gave it away to many charitable causes. Indeed, there are many things in the San Francisco area that are named after him or were made possible by James Lick. But a good fraction of his fortune he wanted to devote to sort of a family monument. And he thought, well, it could be fun to create statues of himself and his parents, like the Moai on Easter Island, and put them up on Ocean Beach, but facing outward to the ocean instead of inland, like the ones on Easter Island. But people told him that, look, if we ever get attacked from the west, these are such obvious targets that they'll be the first things that go down. So that's not such a good idea. So then he said, okay, well, how about a pyramid at the corner of 4th and Market Streets, bigger than the pyramids of Giza? And that would be a family monument. But, you know, he was told pyramids are no big deal. There are pyramids in Central America and Mexico and Egypt. There are pyramids all over the place. And one George Davidson, who at that time was the president of the California Academy of Sciences, apparently convinced him to put a significant fraction of his wealth into a project that would benefit humanity, and in particular, the world's largest, most powerful telescope. And so James Lick, who had no clear interest in astronomy, said, okay, he'll do this as long as it becomes the Lick Observatory, a monument to the family name. So in 1875, he gave this gift of $700,000. I've not inflated this number, okay? It's some tens of millions now if you inflate it. And if you compute the fraction of the GDP that this represented in 1875 compared to now, it's the equivalent of a $1.2 billion gift, okay? To science, to astronomy, to the University of California, which back then was only Cal. Not that I have anything against the rest of you. My own wife and older daughter are graduates of UCLA, but go Bears, okay? So the University of California then was just Cal, and so this became the University of California's Lick Observatory, and the big telescope was built, and the wishes of James Lick were fulfilled. Underneath the base here, below the usually movable floor, is his final resting place. Here lies the body of James Lick, okay? So he really is there. But you might reasonably ask, well, you know, Lick Observatory now is 132 years old. Of what relevance is it other than as a historical monument? And what I hope to tell you in the next half hour is how it remains a vital and productive and in some ways unique facility for research, technology development, education, and public outreach. And part of the reason is that we've kept up with the times, okay? The 36-inch refractor is no longer the big telescope there. Indeed, it's been superseded by telescopes that are equipped with modern cutting-edge detectors. And these aren't even the biggest telescopes in the world now, not even close. There are many much bigger telescopes. But because we equip these telescopes with modern solid state devices, they remain, you know, really, really useful. And, you know, they're smaller than, say, the Keck telescopes, which I have the privilege of using. I cherish my time on the Keck telescopes, but I typically get 1 or 2 nights every 6 months. I just got my allocation a few days ago for the next 6 months, and I got lucky. I got 2 nights. So I'm gonna do something important with that time, but there are certain projects like repetitive observations of the same objects, which I can't do with those telescopes, but I can do them at Lick. So let me give you just 2 examples of the kind of research we do there. The first is dear to my heart, exploding stars, and the second is interesting, but it's not something that I personally work on. It's other planets orbiting other stars, and that's just to show you that I'm trying to be an unbiased presenter here. But first, the thing that's close to my heart, exploding stars. Now, most stars, like our sun, won't explode at the end of their lives. They gradually grow old and will eventually get fried, but not suddenly. But some stars literally explode in a titanic act of self-destruction at the end of their lives, becoming millions or even billions of times as powerful as our sun. Now, here's an example of one such star in a galaxy, a gravitationally bound conglomeration of 100 billion stars, and there's one star exploding. Usually takes a few weeks to brighten and some months to fade. We've sped up the process here so as not to bore you. But here at its peak, you can see that it's as bright as the central few billion stars in this galaxy of stars. So folks, if our sun were to do this, sunblock of 50 just wouldn't cut it. You'd need sunblock or supernova block of 1 billion or so. But don't worry, be happy. We know quite clearly that our sun will not undergo this fate. If it does, you can fire me, even though I'm tenured at Cal. I won't care because being fired will be the least of my worries at that time if the sun blows up, okay? So go ahead and fire me. Anyway, these things are not just spectacular to look at from a distance, but they're important for our very existence, because what a normal star does during its life is it generates energy, of course, but it does so by fusing light elements into heavy elements. So right now, our sun is fusing hydrogen to helium. Later, it'll fuse helium to carbon and oxygen. More massive stars can fuse up to still heavier elements, all the while generating the light, the energy that we see. But if none of the stars ever exploded, then those heavy elements would be forever trapped in the cores of stars, not available as raw material for the production of new stars, planets, and life. But because some stars do explode, they eject these heavy elements into the cosmos and generate additional ones. And these chemically enriched gases go flying out, and we can see supernova remnants like this one that Asian astronomers studied 1,000 years ago. And we can tell that these gases are chemically enriched in elements like the carbon in your cells, the oxygen that you breathe, the calcium in your bones, the iron in your red blood cells. Those elements weren't there, at least not in great quantities, when the star formed. But during its evolution and during the explosion, those elements are generated in the guts of the star and then expelled outward by the explosion. And after 10,000 years or so, the chemically enriched gases expand even more. And then they mix with other chemically enriched gases, eventually forming a gravitationally bound blob like the Orion Nebula in the middle of the sword of the great hunter Orion. And in the central region of a cloud like this, stars have been newly formed and are still forming, okay? And around some of those stars are disks of debris, not just gas, but dust, fine little particles of dirt made out of the chemicals, the elements that many previous generations of stellar birth and death gave rise to. And in these disks, planets can form, rocky, Earth-like planets. This is what happened in our solar system 4.5 billion years ago. And somewhere, somehow, at least on Earth, life formed. We'll leave that to the biologists. They have a much more difficult job than astrophysicists who only deal with inanimate objects. And that life evolved. I'm skipping a few steps here. And it led to sentient creatures who have the curiosity to ask questions, questions about their very existence, and the brains and the mechanical ability with which to build machines to help answer questions, including those of their very origins. Where did the chemicals of our DNA come from? Well, they came from stars. And by the way, here at the model of the DNA molecule at the Lawrence Hall of Science in Berkeley, you can see some of my DNA. I happen to have 4 children. And those of you who have been Lair campers for a long time might remember Zoe Filippenko, who was a staffer for 2 years, about 5 years ago or so. And more recently, Simon, who was a staffer for 3 years, up until about 2 years ago or so. So anyway, these are future Lair staffers, Capri and Orion, but they're still a little bit too young. Anyway, we are made of star stuff, as Carl Sagan used to say so eloquently. That's one of the 5 things I tell my students in my introductory class to remember forever. I'll meet them when they're 97 and I'm only 99, haha. And I'll ask them, where did the elements of which we are made come from? And if they don't say from stars and exploding stars, I will retroactively fail them. And their entire careers will have been shot, okay? That's just a joke, of course, but still, I tell them that. Okay, so we want to find a bunch of these things to figure out what elements they produce and which kinds of stars explode. But in a galaxy like this, a star might explode only every 30 or 50 years. So if I were a really cruel advisor, I would have each of my students staring through the eyepiece of the great Lick refractor until they find an exploding stars. And then we let them graduate and go on to greener pastures, perhaps Stanford or whatever. Just joking, okay? But anyway, no, I can't take unfair advantage of students like this. Students need to study and sleep, and most importantly, they need to party. So even a tenured professor can and should get fired for taking such egregious advantage of unsuspecting students. Fortunately, with modern technology, kind of like what you have in your phones, there are these great detectors that we can stick at the eyepiece end of a telescope. And then all we do is we take photographs of thousands of galaxies and we simply look for arrows. See that? An arrow points to that exploding star and that exploding star and there and there. By rigorous mathematical induction, I conclude that this procedure must work every time. Well, I'm just kidding. Obviously, there aren't, arrows painted in the sky. It's not that easy. What we do is we look at thousands of galaxies with a robotic telescope, a small, by today's standards, but robotic telescope at Lick, which has been programmed to take pictures of over 1,000 galaxies a night. And then it repeats the process and it compares the old picture with the new picture. And usually there's nothing new in the new picture, but occasionally there is. You can see that arrow. Well, okay, we put it in with Photoshop or something, but it's pointing to that little dot that wasn't there a few nights earlier. So that's a supernova candidate. It could be something else. It could be an asteroid with Earth's name written on it, heading toward Earth. And, support your local astronomer because he or she may someday help save humanity. If we find these things 50 years in advance, and then clever engineers and applied physicists figure out how to deflect the rock, they will save humanity. But that's not what my team does. We're interested in the exploding stars. So we throw out the asteroids. So there might be a dozen or 24 candidates out of 1,000 images. And then I use undergraduates with their superior eye-brain combinations, and they look at these candidates and determine which ones are likely to be genuine exploding stars worthy of further consideration by our team. And these students get practice in programming and data analysis and statistics and error propagation, things like that. And these are skills that will serve them well in today's high-tech world at Apple or Google or Microsoft or Facebook or you name it, right? And they get such a thrill of discovery in participating in this supernova search and identifying the exploding stars. So most of them won't go on to become professors of astrophysics, and that's okay. But we serve humanity by getting these students trained and excited about fields that are more immediately useful to society, like medical physics, applied physics, computer science, applied medical physics, things like that. So anyway, so I'm very proud of the decades of students I have had who have worked on this project. Well, we normally have one weekly lunch at which I provide pizza. I provide pizza and they justify their existence for the previous week. And here's a picture from one of my group meetings in January. Nowadays, we hold group meetings via Zoom. This was just a couple of days, I guess this was a week ago. Yeah, anyway, I'm sure many of you, you're used to Zoom meetings as well. So, okay, no pizza. And just to show you how frequently we return to the same galaxies, you can see here a galaxy whose picture we took on July 8th of 2013. And 2 days later, there's the arrow and it's pointing to that dot that used to not be there. So we find these exploding stars really early in their development. And that's very important because a lot of the physics of what's going on, you discern through studies at very early times. So that's really cool. But the point is, to do this kind of work, you need huge amounts of time on small or modest-sized telescopes. If you could try to mute yourselves.
What do you want me to do?
Just mute yourself.
I'm watching it now.
Yeah, you just hit mute at the bottom there.
Right now, there's no red line between.
Thank you. Okay, so I told you I love the Keck telescopes, but by getting only 1 or 2 nights every 6 months, I can't continually go back to those telescopes and examine the same galaxies night after night after night. That's something that can be done with large amounts of time on small or modest-sized telescopes. So there's a type of project that you can do with the facilities at Lick but not bigger, more expensive things. Having found the supernovae, we then use a bigger telescope, still small by today's standards, but 3 meters in diameter, to collect a lot more light from that star and pass the light through a prism. By analyzing the brightness as a function of color or wavelength, you can tell a lot of interesting things like the chemical composition of a star. And by plotting the brightness or the intensity as a function of color or wavelength, blue is right around there, red is right around here, this is the near infrared, you can see the different types of ways in which stars can explode, and you can see the elements that were produced: calcium, oxygen, silicon, sulfur, iron, magnesium, more calcium. So this is how we can tell what the star is made of. And a single spectrum like this gives you just a snapshot of the chemical composition of the outermost parts of the star. But if I can get lots and lots of spectra over many nights, then without looking at the details here, just notice that the character of the spectrum here looks very different from down there. And what you're seeing is the spectrum as the supernova evolves in time. You get like a CAT scan. As the gases expand out, they become thinner and more transparent, and you can see down into the inside of the star. Here you can see that there's silicon and calcium and things like that in the outer parts of the star. And these little wiggles here are caused by iron. So the iron is produced deep in the core. So this is like a CAT scan. But no one gets enough time, this is measured in days, on a single telescope to do this kind of work on the big telescopes. But here I can call up my friends and I can say, hey, do me a favor, please. We're studying this really interesting supernova, and my friends are happy to do me a favor, and I'll repay them or make them a co-author on the paper. But on the biggest telescopes where the time is so hard to get, they might say, you know, that's a great project, but I had to fight tooth and nail to get this one night, so I've got to do my own projects. And that's a completely reasonable perspective. But when you have lots of time, people are much more collaborative, much more cooperative. Moreover, to get brightness versus time like this, notice we can get data every night or nearly every night. And again, this tells us something about the physics of what's going on when you plot the brightness versus time. And we can do this because we have access to, again, small telescopes, the 1 meter nickel telescope at Lick Observatory, which is used primarily by students. And it used to be that I'd have a hard time getting my students up there because they don't have cars and they can't rent a car and they have classes to take. And even from Berkeley and Santa Cruz, it's a 4-hour round trip. And from UCLA and San Diego and Irvine and Santa Barbara, they would have to fly and rent a car. So it would be hard to get students up there in the past. But for the last decade or so, each of the UC campuses has had these remote observing rooms set up in their physics and astronomy building, where we have a quick internet connection with Lick Observatory. And so the students can be running the telescope from their home campuses. And now during COVID-19, we've even made it possible for people to run the telescopes from home. I mean, it's fantastic. So this means there's a big increase in student involvement. I now have, as you saw in that picture, a dozen or even 15 students in my group, because now I can really involve them in the guts of the project, taking data, analyzing data, not just doing what I tell them to do with data that I took a decade ago. They can feel much, much more involved. So this has really been fantastic for the undergraduates especially. Well, again, to get these brightness versus time curves, or the CAT scans of the chemical composition, you need huge amounts of time on modest-sized telescopes. There's going to be a quiz at the end. 2 questions. You know, where did the heavy elements in your body come from? Stars. And, you know, for what kinds of projects are the telescopes at Lick good for? For the kinds of projects where you need repetitive observations of the same objects, okay? So that's my research. But then the other area, which is in the news all the time, but I don't happen to work on it, is exoplanets, planets orbiting other stars. And what my colleagues are trying to do is answer this age-old question: are there other planetary systems, or any of them like our own solar system? And you know, it's hard to see a planet directly from the glare of the star that it orbits, because it's so much smaller and it reflects only a little bit of light. But remember, planets orbit stars, and that means the star moves as well. It's more correct to say that they orbit their common center of mass, which I've shown right here. And what that means is that when the planet is coming toward us, the star is going a little bit away from us. And if you monitor the spectrum of the star, you can tell whether the light is Doppler blue shifted or Doppler red shifted. It's blue shifted when it's coming toward you, kind of like when a siren is coming toward you, the pitch sounds high, right? And when the siren is going away from you, it sounds low. So when you hear the siren going past, it goes ee-yaw, like that. Well, here the star is going ee-yaw, 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 because it's going around in its orbit. And when you spread the light out into a spectrum that's very much dispersed like this, that is, we spread it out a lot, and you look in detail at these so-called absorption lines, which are produced by chemical elements in the atmosphere of the star, you can see that those absorption lines shift to shorter wavelengths, bluer wavelengths, and longer wavelengths, redder wavelengths. And here we've exaggerated the effect by a factor of 1,000. But you can see that the light levels in these pixels are changing ever so slightly. And you might say, well, if the effect is exaggerated by a factor of 1,000 here, how are you ever going to see it? Well, remember, there are thousands, even tens of thousands of lines in the spectrum that are all doing the same thing. And so we can detect motions as slow as though you were walking. It's as though the star is walking, a meter per second or something like that. Even 10 centimeters per second. That's a slow walk. We can detect that now. And to just give you a plot here, here's speeds in meters per second versus time. My colleagues noted that this star, Upsilon Andromedae, is not standing still. You can see these points are not all at the same speed. So they suspected that it might be orbited by a planet. So they got a lot of data, and sure enough, it's going back and forth. And then they got really a lot of data to really make sure that, yeah, there's a planet orbiting it. A planet orbiting with a period of roughly 7/10 of a year. And that planet has a mass twice of Jupiter. You can use Newton's laws to figure that out. And then you see that there's also a 4-year periodicity here. See that? And that's caused by a planet having, coincidentally, 4 times the mass of Jupiter orbiting. So that's 2 planets orbiting Upsilon Andromedae. And what I haven't shown you here is the back and forth motion caused by a small planet with a 4.6-day orbital period. So if you were to superpose this on our own solar system, here's Earth's orbit, Venus's orbit, and Mercury's orbit. Okay, here's the more or less normal planets out here, but there's this weird one here that it's orbiting very, very close. That's unlike anything we have in our own solar system. Mercury is way farther out, and these are the so-called hot Jupiters. They're hot because they're very close in, and they're pretty massive like Jupiter. This one is at least 60% of the mass of Jupiter. And that was a type of planet that simply wasn't known by studying our own solar system. In fact, it's so close to the star that the star is evaporating the planet. It's eating it alive. And here's an artist's impression of what the star might be doing to the planet. Someday the planet will no longer exist. You know, take that, said the star. Well, again, to get data points like the ones I showed you, the mantra is you need huge amounts of time on modest-sized telescopes. And 70 of the first 100 discovered exoplanets were found with this 3-meter telescope at Lick. So that's really, you know, a fantastic feather in our hat of the University of California. But now, you know, people are wondering, is anybody out there, right? This is mid-1990s, and discovery of 2 planets brings us closer to solving the most profound mystery of the cosmos. You know, planets, that's great, but, you know, is anyone out there? And you might think, well, you know, various publications that you've read have already told you that there's evidence out there. Look, alien backs Clinton. I'm happy to he saw through Bush and Ross Perot. And then same type of alien then switched political allegiance, I guess. Hasta la vista, Gray Davis. I don't think I need to tell Cal alumni and their associates that you shouldn't believe everything that you read, right? There is such a thing as fake news. Anyway, it's an interesting question. You know, are there creatures out there, especially intelligent ones? And when you've only found gaseous Jupiter-like planets, you know, that's kind of cool, but those are not the kinds of planets that have a surface with liquid water and continents and things like that. No, what really we want are Earth-like planets, right? With a solid surface and some water and continents and things like that. But of course, Earth is a tiny planet compared to Jupiter. The reflex motion that Earth produces in the sun is only about 10 centimeters per second, whereas Jupiter produces a motion of 10 meters per second. That's 100 times smaller. So it's hard to detect Earths. You need really a lot of data to detect little planets, especially little planets that are not so close to the star that the water evaporates away. You know, you want ones that are not so close that they're too hot, not so far away that they're too cold, all the water is ice. You want the Earth-like planets in the Goldilocks zone, right? Too hot, too cold. We call it the Goldilocks zone because it's just right, like the porridge that Goldilocks settled on, right? Or no, that the 3 bears settled on. Anyway, I've forgotten the story. But to detect those little tiny planets, you need really huge amounts of time. Every night on modest-sized telescopes, because 10 centimeter per second motions are very difficult to detect. Even 10 meters per second wasn't easy. It wasn't done until the mid-1990s. So my colleagues said, well, we want every night on the Lick 120-inch 3-meter telescope. And I and other astronomers said, well, you know, exoplanets are important, but we have our own projects too, so no. So they said, okay, we'll build our own telescope. And so the most recent telescope at Lick Observatory is nearly as big as the 3-meter. It's in fact just as big as the Hubble Space Telescope. It's called the Automated Planet Finder. And it robotically, like my Kate telescope, takes spectra of bright nearby stars every night, searching for Earth-like planets. And just like I study bright supernovae, exploding stars that aren't so affected by the city lights of San Jose and the greater San Francisco Bay Area, they study naked eye, bright stars. And so, of course, we would prefer skies to be dark, but look, you know, we have this observatory near a large metropolitan area, and we're not about to turn off the lights. No one is, right? So what we do at Lick are the kinds of projects that are not affected very much by the city lights, and looking at bright stars is one such project. So we're especially keen on doing this now because there's a NASA satellite called TESS that is finding exoplanets using a different technique, which gives their size, their radius. But the Doppler technique, the wobbling around technique, gives you the mass. And the mass divided by the volume gives you a density. And that's really interesting because that allows you to distinguish rocky Earth-like planets from gaseous giants like Jupiter. So that's kind of cool. And then here's one of our recent graduates, Lauren Weiss, whose project was to look for Earth-like planets around the 100 or so most nearby stars that are only 20 light years from Earth. Now, a light year is the distance light travels in a year. It's 6 million miles. So it's not exactly nearby, but it's nearby for an astronomer, okay? I, in some of my research, deal with exploding stars that are literally billions of light years away. Well, these stars are only 20 light years away. And the idea is that if we find Earth-like planets around the nearest stars, we could let loose our arsenal of telescopes over a variety of wavelengths, including radio wavelengths, and try to detect, you know, possible communications from these aliens. And maybe with this technique someday, we'll find Yoda or ET or whatever, right? So that's the goal. Very quickly, because I'm running out of time and I want time for questions, let me tell you about technology development. It's much smarter and cheaper to develop new technology on inexpensive telescopes, perfect it, and then move it over to the big guns. You don't want to be tightening screws and decoding software on the Keck telescopes, each of which costs about $50,000 a night to run. You want to do it on a less expensive telescope. So that's what we do at Lick. And our best example, though by no means the only one, is something called laser guide star adaptive optics. You've all seen stars twinkle. They twinkle because of turbulence in Earth's atmosphere. But this also makes the stars look blurry if you look at them through a big enough telescope. And that's because there are many turbulent pockets of air in Earth's atmosphere. Well, if you look at a star tens or hundreds of times a second, you can see that at any given instant, it actually consists of a bunch of little tiny dots called speckles that are all moving around and changing. It should look like this, but it looks like that. So knowing that it should look like this, you can do a correction using both hardware and software to make it look like that. And this technique was developed largely by Claire Max, who's now the director of the University of California Observatories. She was at Lawrence Livermore Labs when this was developed, this technique for the military, and then eventually it became declassified, and now we can use it in the universities. But the basic idea is you take pictures hundreds of times per second, correct the star's appearance to what it should be. That then corrects anything within a small patch of sky next to the star. So suppose you have a galaxy that looks fuzzy next to a bright star. You look at the star hundreds of times per second, correct it, and then the corrected image of the star also gives you a corrected image of the nearby galaxy. So it might look like this. Now, this picture was actually taken with the Hubble telescope, so I'm cheating, but I'll show you some real examples in a minute. So that's really a great technique. It's called adaptive optics. But what about the laser? Well, here's where the laser comes in. You might say most of these galaxies, all these little blobs or distant galaxies, most of them don't have a star next to them. Here's one that does have a star. So you might say adaptive optics works for this one, but it doesn't work for that one and doesn't work for most of the ones here. Well, that's where the laser comes in. We can fire a laser along the axis of the 3-meter telescope and create a fake star, not to be confused with fake news, in a layer of sodium that's about 100 kilometers up above Earth's surface. That sodium is actually deposited there by little meteors that come in. And you can make the sodium glow, and that produces an artificial star. You can make that star be next to any galaxy you want. And if you take hundreds of pictures per second of that star, correct it so it looks like a point, then each of your galaxies will be corrected, whichever one you're pointing it next to. So that's the laser guide star adaptive optics. That was developed and perfected at Lick and then ported over to the world's greatest telescopes, the Keck 10-meter telescope, which again, as I said, University of California astronomers have the privilege of using. And those telescopes now, equipped with laser guide star adaptive optics, are the greatest telescopes at this technique. They've had the most important results using this technique, which was developed and perfected at Lick. And we're now going through the process of making it even better at Lick before moving it over to Keck. And just to show you a couple of examples, this is from Professor Imke de Potter, a colleague of mine at Cal. Here's a picture of Io, one of the Galilean moons of Jupiter. So Galileo saw this 400 years ago, before adaptive optics and after adaptive optics. So here you can see all these little blobs. These are active volcanoes. Io is the most volcanically active body in our solar system, and I won't go into that right now. Basically, it's being pushed and pulled by big bully Jupiter. Then there's Uranus, the 7th planet from the sun, and that is the correct pronunciation for anyone above the age of 7 or so, before adaptive optics and after adaptive optics. You can see the rings, so Saturn is not the only planet with rings, and here you can see the development of a storm. And it's by studying storm systems on other planets that we can come to a better understanding of Earth's climate. Now, I'll be the first to admit that Earth is a lot more complicated because it has oceans and continents. Nevertheless, studies of other atmospheres are leading to a better understanding of Earth's atmosphere and climate change and things like that. Indeed, Venus went through a runaway greenhouse effect long, long ago, and presumably Earth won't go through a runaway even if we do have rising temperatures. Venus was special in that regard. Nevertheless, you don't need a runaway for things to become kind of bad. So, and then my favorite example using laser guide star adaptive optics by Andrea Ghez at UCLA and also a colleague of mine, Reinhard Genzel at Berkeley. This is the center of our galaxy before adaptive optics and after adaptive optics. An amazing difference. And by studying the stars in that central blue square for 20 years, they have seen the stars moving around. Zoom! Look at that. I especially like the orbit, well, 2 of them. I like this one here because it's gone through more than one full orbit. And I like this one here. Watch this one coming in from the upper left. Zoom! These stars are coming within a very short distance from some giant mass, 4 million times the mass of the sun, indicated by this little 5-pointed star there. But really it's dark, it's black. You can see the year in the upper right here. So this is 20 years worth of data. This thing is very gravitationally attractive, but dark. So we've concluded that this is a black hole, a region where gravity is so strong that nothing, not even light, can escape. All right. And this is among the best pieces of evidence we have for black holes. It's really fantastic. Very quickly, public outreach. You know, Lick is the primary base for astronomy education and outreach efforts for the University of California. I mean, sure, we have Keck too, but most people who go out to Hawaii do that to sip a Mai Tai on the beach. And, you know, if you go up to nearly 14,000 feet, it's cold, it's windy, it's hard to breathe, and it's hard to think. So it's better to sip Mai Tais on the beach. But these domes you can see from Silicon Valley. So we have lots and lots of visitors, over 25,000 a year, private groups, which we've had to basically cancel for the foreseeable future, and even public visitors are not allowed there. We're allowed to continue operating some of the science with the robotic telescopes, but some of the science with telescopes that require an operator is still not going. We're hoping to start soon. But anyway, in a normal year, we have lots of visitors. There's a hallway where there are all these video displays and stuff where various jokers describe their research. And then we have a whole cadre of volunteers who show people things through the great refractor. And on a normal summer, well in advance, sometime in the spring, go to ucolick.org or just Google or whatever your favorite search engine is, Lick Observatory Public Summer Program, and it'll land you on that page. But you can get the free tickets to look through the telescope. And there's also a program called Music of the Spheres, where we have a concert up there. And there the tickets are not very much because we pay the people who play the concert. So it's really fun. We also set up telescope outside, which again inspires youth, sparks interest. These are, if not future professional astrophysicists, some of them are, I think, certainly future people who will be involved in technology and engineering and computer science and physics and programming and things like that. So here we're looking at the sun safely. So these are all great things: the public outreach, the technology development, training of grad students and postdocs, and the projects that can't be done anywhere else. But just to finish off, there's often a but at the end. In September of 23, the UC Office of the President, under great financial strain, I mean, I understood their pain, they decided to tighten belts throughout the UC system, and that's happening now too, right? But they decided to reduce the funding of LIC in 2016 to be ramped down to 0 by basically 2 summers ago. So that's a bad idea given all that we do. I mean, I understand tightening belts, we all have to, okay? But ramping down something to 0 when it's the very observatory that serves the students. For whom is the University of California if not for the students, right? That's just a bad idea. And for the public stuff we do. So we started educating the Office of the President on what it is that we do and why we're worthwhile. To some extent, it was our fault that we hadn't properly educated them. But, you know, Janet Napolitano and Amy Dorr and others listened to us and they understood. So within about a year, they said, okay, we'll provide you partial funding, but you know, you're going to have to seek your own funding as well because we do have to tighten belts, okay? So we'd like to become largely independent of the UC Office of the President because, you know, they're at the mercy of the state legislature, and who knows what'll happen now with COVID-19. There are new cuts coming. Indeed, UCOP recently warned us that we're going to experience an additional cut of 10%. They're just trying to figure out how much. That's about $250K. Takes about $2.5 million a year to run this facility. So we're now quaking in our boots, but they just warned us, so we have some time to try to, you know, raise some money. Now, some years ago, I was able to get a gift through Google, a new branch of them called the Making in Science branch. They understand that public education in science and technology is really important. And, you know, the 15-year-olds of today are the Googlers in a decade, and the 8-year-olds of today are the Googlers of, you know, 15 to 20 years from now. So they understand the importance of public education in science. And so they gave a gift of $1.5 million. And they said, you know, we're hopeful that you'll be able to use our credibility, our stamp of approval, to help raise matching donations. So we've been doing that slowly but surely. Now we've got to do it a little bit more quickly now because of this further cut that the UC Office of the President has promised us. These donations can also be used for student and postdoc fellowships. I've set up a thing called the UC Berkeley Lick Observatory Operations Fund, but it can be used to fund students and postdocs as well, those who will actually be doing science with the observatory. And those same students and postdocs go up and they serve as docents and educate the public and that kind of stuff. So, you know, small amounts from a lot of people can add up to a lot, or large amounts from a small number of people. And usually it's a combination of things. So, you know, the give.berkeley.edu website, with which many of you are familiar from Giving Tuesday and things like that, just stick LIC in the search box and it'll land you on the right page. Or if you know of a particularly big gift that someone else might want to give and they need to talk to someone, feel free to contact me whenever you'd like. The other thing is that if you donate soon, I am going to have this summer several Q&A sessions for donors of mine. And by mine, I mean not just my own research group, but Lick Observatory as well. And I will contact you for a private Q&A session, not necessarily one-on-one, but a very limited number of people at any given time. And so I'll be very, very happy to take questions now, but If you want even more questions answered, then, you know, if you'd like, feel free to give. So thank you very, very much. I'm sorry we got a late start, partly because of my fault, but I'm happy to take questions as long as Kathy and Mike and others at the Lair allow me to. So thanks very much, and go Bears.
Awesome. Thanks you, Alex. We do have a few questions that have come through the chat, so I'll start there. First question is, how do you and other astronomers feel about the potential of 12,000 Starlink satellites orbiting Earth? Will they really block your view? And if so, is it worth it?
Yeah. So great question. Here's the rub. It's not 12,000. It's more like 100,000 when you include the fact that there are other companies besides Elon Musk's Starlink who want to do this and have begun doing this, okay? So it's like 100,000 satellites. And I understand the goal, right? To bring the internet to, you know, the isolated, often low income parts of the world. Indeed, Google had a project for a while called the Loon Project, where they were going to have a bunch of balloons. I haven't heard much about it lately. Maybe it's still being done, but the problem was it was hard to keep the balloons where you want them to be. In particular, you needed the balloons over the major cities that would beam up the data, and then the data would spread out to all these other balloons. But the satellites, yeah, great idea. I understand and applaud in many ways. However, for wide angle pictures of the sky surveys that are being done, for example, or will be done by the Vera Rubin telescope, an 8-meter telescope that's being built in Chile now, the brightness of those satellites is going to clobber our images. And I've seen them. They're among the brightest stars in the sky. You can see sometimes they get launched, and when they're in their holding pattern about 280 kilometers, or maybe it's miles, I don't remember, up, they're really bright. And then when they go to double that distance, they're still detectable, not so easily by eye, but with big telescopes, yeah. So we've gotten Elon Musk to listen to us recently, and they're going to be painting them black and having shields and things. That'll decrease their brightness, so that'll mitigate the problem to some extent. In part, we'll also have to modify how we take our data, maybe take more frequently pictures of the same parts of the sky. And then what you do is you filter them. You compare let's say you have 5 images, and 4 of the 5 don't have a streak in one place, and the 5th one does. You know that the streak then is a satellite, and you replace the part with a streak with the data from the 4 that don't have streaks. So we will find a way to mitigate this, but when they were super bright, they basically blast the electronic chip that's in your phone or whatever, and they saturate the whole thing. It's like exposing your phone to the sun, right? It kind of blasts the whole thing. It ruins your photo. So good question. For narrow fields of view, where I'm looking at one particular supernova or a little tiny galaxy, or I'm trying to find an exoplanet, that's not such a big deal because these satellites don't fill most of the sky. But if you like looking at the constellations unadulterated by satellites, look soon, because someday the satellites might be more numerous than the naked eye stars. And I know that at the star parties at the Lair, in the past, we've gotten a kick when we've seen a satellite, sometimes even the International Space Station or the Hubble Space Telescope. But soon it's going to be passé, because there's going to be as many satellites as there are stars.
Very good, very good. Next question is, do you personally believe that aliens exist somewhere, or do you think it's just made up?
Yeah, so that's a great question, and I'll give you my short answer because it's a long and complicated topic. I think for a number of reasons that intelligent beings of our intelligence, creativity, and mechanical capability are very rare, maybe one such thing or a handful per Milky Way galaxy. So I'm not saying we're alone, but I think we're quite rare, not hundreds of thousands in our Milky Way like Carl Sagan thought, but also not we're the only ones, you know, but rare. And the reason I think that, it's numerous, but one of the reasons is that there's been, 10 billion plus species of life on Earth, and there's no evidence that any other life has gotten anywhere near our level of intelligence, curiosity, and mechanical ability. Second of all, we came along only recently in Earth's history. Homo sapiens, 250,000 years. Early hominids, 4 or 5 million years. So throughout most of the history of Earth, and even most of the history of life on Earth that's fairly complex, the Cambrian explosion 540 million years ago, over most of that history, an intelligent alien flying past would have said, there's nothing particularly intelligent or mechanically able on Earth. And third of all, though our intelligence has certainly improved the lives of hundreds of millions of people in the last century, you look at China, for example, forgetting about the long-term harm like the PM 2.5 particulates and things, nevertheless, it is true that China has lifted hundreds of millions of people out of poverty. It's not at all clear to me that our intelligence is a long-term benefit, a long-term evolutionary benefit. That is, we're the first species that can, and perhaps someday will, deliberately or inadvertently destroy ourselves and much of everything else. And so, that bodes ill if you think that, we've been in the nuclear or even the industrial era for only a short time, 100 or 200 years, and, we're already capable of destroying ourselves. Now, we could also use that intelligence to save ourselves, but I would say it's unlikely that we're at the beginning of a very long and prosperous future. It's more likely that we're somewhere near the middle. And if you're a pessimist like that, well, we have a couple of 100 years to go if you ask yourself, how long has it been since the Industrial Revolution? Or even if you say, well, how long has it been since Homo sapiens came along? In the grand scheme of things, we only have 250,000 years to go. So anyway, and then finally, not finally, but another argument is that if aliens were really common, then it turns out some of them you would expect would reach a level of technological ability that would allow travel among many stars. And once you get to that point, it actually doesn't take long to populate much of the galaxy. And so the question then is, and this is known as Fermi's paradox, if they're common, why don't we have good evidence for them? Area 54 or 53 and Roswell set aside, those don't quite clear the standards of evidence that scientists demand these days. So that's my basic answer. I think we're rare, but not alone. But I don't know, so we should keep looking.
Very good. Next question from a camper says, my 10-year-old daughter wants to know if you think one day we will be able to travel near the speed of light.
Yeah, very unlikely. And by that, I mean we, humans, in rocket ships. We've already sent subatomic particles like electrons and protons at very close to the speed of light. There's the very famous Large Hadron Collider on the border of Switzerland and France that accelerates protons to very nearly the speed of light. The problem is that you need vast amounts of energy to do even that, to accelerate a subatomic particle to nearly the speed of light. If you take us and you include the rocket ship that houses us, and you include the fuel that would propel us and all that, the energy requirements become almost unfathomable. I mean, it's like, converting a whole city into pure energy, forget about all the people and the buildings and all that from which the energy came. So no, I think the answer is no, sadly.
Okay, next question is, other than the Great Courses program on understanding the universe, what resources would you recommend for an interested novice who wants to learn more about this topic?
Oh yeah, so well, one thing I've been doing a lot of the past 3 months is listening to podcasts and watching videos and stuff, even as I run or walk or get exercise, you know. So there are tons of great videos out there. You go to YouTube, and if you happen to like me, you can type in my name. There are lots of free videos out there. People like Brian Greene, and I should point out that I've been just nerding out on World Science Festival that Brian Greene co-organizes in New York City each year. I don't think they had it this year. But anyway, all those things are recorded and they're out there. I recently gave a talk to the Commonwealth Club during COVID-19. They're making all their stuff available, maybe even beyond. Maybe a good sort of after effect of COVID-19 is that lots and lots of really good educational material is up there for free now. And Commonwealth Club talks are really good, you know, because they get good people. They screen their people. It's not just someone mouthing off to YouTube, right? And then there's, if you're the book sort, you know, there are lots of good books out there, popular books, but like Neil deGrasse Tyson has lots of nice books on astronomy for beginners and things like that. His latest one is Letters to an Astrophysicist or something like that. I have a more sort of high school level, beginning introductory college level book called The Cosmos, Astronomy in the New Millennium, written with Jay Pasakoff of Williams College. That's the book I use in my introductory astronomy class at Cal, but dedicated high school or even middle school students should be able to understand it. So there's tons of stuff. And then on the online, if you go to things like science.com is really good, or, you know, astronomy in particular, there's Sky and Telescope magazine and Astronomy magazine, lots and lots of stuff available online. Yeah.
Okay. Again, anybody feel free to put questions in the chat. Alex, you know, what do you think of the SpaceX program and specifically getting to Mars? What does that mean for your people in your field, and what will that allow astronomers to do more of?
Yeah, I wouldn't have expected any worse question. I mean, first of all, there's no such thing as a bad question, but what I'm saying is I could expect a Cal audience to ask such questions. You know, so getting to Mars is hard. It's going to cost a lot of money, but part of what makes us human is this desire to explore, to be the pioneers, right? To explore new worlds. And of course, another new world is the ocean, right? There's much of the ocean that is unexplored too. But if you go away from Earth, well, you know, we've gotten to the moon. The next nearest thing is Mars, other than Venus. Venus gets near sometimes, but Venus is not very hospitable. Venus has 92 atmospheres of pressure beating down on it. So it's like if you're a diver, if you go down to like a kilometer or so underneath the ocean surface, that's the kind of pressure you feel. I don't recommend going down a kilometer, okay? Most divers are certified to something like, you know, 25 to 40 meters, all right? So it's really huge pressures, and along with that comes enormous temperatures. You could melt lead on the surface of Venus, and it's because it's got this runaway greenhouse effect, which traps a lot of the energy because of the carbon dioxide in the atmosphere, okay? So Venus is not very hospitable. Now Mars is kind of cold overall, but it's not bad near the equator. It actually reaches, you know, nice temperatures. And moreover, there's water ice in the permafrost and at the polar caps. And you can imagine tapping into that ice and, you know, building domes and maybe even terraforming Mars. So you could imagine, at the very least, exploring Mars with humans and possibly even terraforming it or partially terraforming it so that some of us could live there. And then you could say that, well, we want to preserve Earth, and, you know, we should do our darndest to preserve Earth. But if something were to go drastically wrong, either because of our own fault or some asteroid or something, and destroys all of humanity, if we have our seeds elsewhere, well, we could give it another go, right? So those are some of the arguments. We have to be, of course, very careful because there could be microbial life of an independent origin on Mars that is not related to Earth. And if we could find it and identify it, that would mean that at least primitive organisms are nearly everywhere, because if they're in two independent places in our solar system, that means it's not that hard to get at least primitive life, bacteria and microbes. And then there's still the question of how often it becomes intelligent and curious, right? So we still have to make sure that we don't pollute Mars and stuff. Now, having said all that, I'm a little bit of two minds, all right? I can see the pros, but I don't think that most of our available funds, and if you look at the slice of the federal discretion, the discretionary funding, that's the slice of the federal pie, it's very small. And there's a lot of astrophysics and other forms of science, biology and stuff that can be done here from the ground or from the International Space Station or whatever. I don't want the missions to Mars to suck up all the federal funds, all right? Because I just don't think that's a smart thing to do. I think most of the science should still be done here, and most of the funding should still be done here. But if you combine the private enterprise with the federal government, that may be the best solution. You know, already SpaceX has delivered, you know, just recently, people to the International Space Station. So we're no longer dependent on the Soyuz rockets, the Russians. And looking at how quickly the private enterprise can go, where, you know, there's some money that can be made, and it's also much more efficient than many government things. I mean, I'm sorry to anyone who's a government employee. I hope I'm not saying anything mean or anything, but, you know, I think people understand that government programs are often inefficient compared to the private enterprise. So it could be that, you know, Musk and Bezos and the Virgin Galactic, what's his name? Virgin Galactica. The third guy who's doing this. Anyway, they are achieving amazing successes, and, you know, reusable rockets and things like that. And so I could imagine that humans might get to Mars within a few decades, something like that. But I don't favor the federal government spending all of its money on that enterprise, all the science money, okay?
All right. Well, that's comes to the end of the questions from the chat box, and we have run over a little bit. And Alex, really appreciate you taking the extra time, and what a great way to start off our guest speaker program here at the Lair. Thank you to everybody who signed in. Like I said, 150 people signed up to join us tonight. And Alex, we really, really appreciate your time, and we look forward to having you back for your next star party at the Camp Gold softball field. And
well, I'm looking forward to it too. You know, I mean, you know, I really miss all that. You know. Oh, Richard, I just saw the chat box, but Richard Branson, thank you, Shauna Sonnenschein. Yeah, Richard Branson, Jeff Bezos, and Elon Musk, of course, right? So anyway, yeah, thank you to all the thanks and stuff. If there are other questions there that happen to come up, and I realize we've run out of time, if Mike or Kathy, whoever's the host, if you'll send me the group Zoom chat, I will try to privately respond to the people who put in some chats here.
That's great. Well,
okay. We
really appreciate it, Alex, and thank you for your time. And everybody out there, go Bears.
Well, thank you. Go Bears. Thank you.
Go Bears.
Bye-bye.